Python has many different kinds of data types: integers, floats, strings, lists, dictionaries, booleans. In Python, each is an object. Every object has the following: a type, internal representation, a set of functions called methods to interact with the data. An object is an instance of a particular type. For example, we have two types, type 1 and type 2. We can have several objects of type 1 as shown in yellow. Each object is an instance of type 1. We also have several objects of type 2 shown in green. Each object is an instance of type 2. Let's do several less abstract examples. Every time we create an integer, we are creating an instance of type integer, or we are creating an integer object. In this case, we are creating 5 instances of type integer or 5 integer objects. Similarly, every time we create a list, we are creating an instance of type list, or we are creating a list object. In this case, we are creating 5 instances of type list or 5 list objects. We can find out the type of an object by using the type command. In this case, we have an object of type list. We have an object of type integer. We have an object of type string. Finally, we have an object of type dictionary. A class or type's methods are functions that every instance of that class or type provides. It's how you interact with the object. We have been using methods all this time, for example, on lists. Sorting is an example of a method that interacts with the data in the object. Consider the list ratings. The data is a series of numbers contained within the list. The method sort will change the data within the object. We call the method by adding a period at the end of the object's name, and the method's name we would like to call with parentheses. We have the ratings list represented in orange. The data contained in the list is a sequence of numbers. We call the sort method. This changes the data contained in the object. You can say it changes the state of the object. We can call the reverse method on the list, changing the list again. We call the method reversing the order of the sequence within the object. In many cases, you don't have to know the inner workings of the class and its methods. You just have to know how to use them. Next, we will cover how to construct your own classes. You can create your own type or class in Python. In this section, you will create a class. The class has data attributes. The class has methods. We then create instances of that class or objects. The class data attributes define the class. Let's create 2 classes. The first class will be a circle. The second will be a rectangle. Let's think about what constitutes a circle. Examining this image, all we need is a radius to define a circle, and let's add color to make it easier to distinguish between different instances of the class later. Therefore, our class data attributes are radius and color. Similarly, examining the image in order to define a rectangle, we need the height and width. We will also add color to distinguish between instances later. Therefore, the data attributes are color, height, and width. To create the class circle, you will need to include the class definition. This tells Python you are creating your own class, the name of the class. For this course in parentheses, you will always place the term object. This is the parent of the class. For the class rectangle, we change the name of the class, but the rest is kept the same. Classes are outlines we have to set the attributes to create objects. We can create an object that is an instance of type circle. The color data attribute is red, and the data attribute radius is 4. We can also create a second object that is an instance of type circle. In this case, the color data attribute is green, and the data attribute radius is 2. We can also create an object that is an instance of type rectangle. The color data attribute is blue, and the data attribute of height and width is 2. The second object is also an instance of type rectangle. In this case, the color data attribute is yellow, and the height is 1, and the width is 3. We now have different objects of class circle or type circle. We also have different objects of class rectangle or type rectangle. Let us continue building the circle class in Python. We define our class. We then initialize each instance of the class with data attributes, radius, and color using the class constructor. The function init is a constructor. It's a special function that tells Python you are making a new class. There are other special functions in Python to make more complex classes. The radius and color parameters are used to initialize the radius and color data attributes of the class instance. The self parameter refers to the newly created instance of the class. The parameters radius and color can be used in the constructor's body to access the values passed to the class constructor when the class is constructed. We can set the value of the radius and color data attributes to the values passed to the constructor method. Similarly, we can define the class rectangle in Python. The name of the class is different. This time, the class data attributes are color, height, and width. After we have created the class, in order to create an object of class circle, we introduce a variable. This will be the name of the object. We create the object by using the object constructor. The object constructor consists of the name of the class, as well as the parameters. These are the data attributes. When we create a circle object, we call the code like a function. The arguments passed to the circle constructor are used to initialize the data attributes of the newly created circle instance. It is helpful to think of self as a box that contains all the data attributes of the object. Typing the object's name followed by a dot and the data attribute name gives us the data attribute value, for example, radius. In this case, the radius is 10. We can do the same for color. We can see the relationship between the self parameter and the object. In Python, we can also set or change the data attribute directly, typing the object's name followed by a dot and the data attribute name, and set it equal to the corresponding value. We can verify that the color data attribute has changed. Usually, in order to change the data in an object, we define methods in the class. Let's discuss methods. We have seen how data attributes consist of the data defining the objects. Methods are functions that interact and change the data attributes, changing or using the data attributes of the object. Let's say we would like to change the size of a circle. This involves changing the radius attribute. We add a method addRadius to the class circle. The method is a function that requires the self as well as other parameters. In this case, we are going to add a value to the radius. We denote that value as r. We are going to add r to the data attribute radius. Let's see how this part of the code works when we create an object and call the addRadius method. As before, we create an object with the object constructor. We pass two arguments to the constructor. The radius is set to 2 and the color is set to red. In the constructor's body, the data attributes are set. We can use the box analogy to see the current state of the object. We call the method by adding a dot followed by the method name in parentheses. In this case, the argument of the function is the amount we would like to add. We do not need to worry about the self parameter when calling the method. Just like with the constructor, Python will take care of that for us. In many cases, there may not be any parameters other than self specified in the method's definition, so we don't pass any arguments when calling the function. Internally, the method is called with a value of 8 and the proper self object. The method assigns a new value to self.radius. This changes the object, in particular the radius data attribute. When we call the addRadius method, this changes the object by changing the value of the radius data attribute. We can add default values to the parameters of a class's constructor. In the labs, we also create the method called drawCircle. See the lab for the implementation of drawCircle. In the labs, we can create a new object of type circle using the constructor. The color will be red and the radius will be 3. We can access the data attribute radius. We can access the attribute color. Finally, we can use the method drawCircle to draw the circle. Similarly, we can create a new object of type circle. We can access the data attribute of radius. We can access the data attribute color. We can use the method drawCircle to draw the circle. In summary, we have created an object of class circle called redCircle with a radius attribute of 3 and a color attribute of red. We also created an object of class circle called blueCircle with a radius attribute of 10 and a color attribute of blue. In the lab, we have a similar class for rectangle. We can create a new object of type rectangle using the constructor. We can access a data attribute of height. We can also access the data attribute of width. We can do the same for the data attribute of color. We can use the method drawRectangle to draw the rectangle. So we have a class, an object that is a realization or instantiation of that class. For example, we can create two objects of class circle or two objects of class rectangle. The dir function is useful for obtaining the list of data attributes and methods associated with a class. The object you're interested in is passed as an argument. The return value is a list of that object's data attributes. The attributes surrounded by underscores are for internal use, and you shouldn't have to worry about them. The regular-looking attributes are the ones you should concern yourself with. These are the object's methods and data attributes. There is a lot more you can do with objects in Python. Check python.org for more info. We will use Python's open function to get a file object. We can apply a method to that object to read data from the file. We can open the file example1.txt as follows. We use the open function. The first argument is the file path. This is made up of the file name and the file directory. The second parameter is the mode. Common values used include R for reading, W for writing, and A for appending. We will use R for reading. Finally, we have the file object. We can now use the file object to obtain information about the file. We can use the data attribute name to get the name of the file. The result is a string that contains the name of the file. We can see what mode the object is in using the data attribute mode, and R is shown representing read. You should always close the file object using the method close. This may get tedious sometimes, so let's use the with statement. Using a with statement to open the file is better practice because it automatically closes the file. The code will run everything in the indent block, then closes the file. This code reads the file example1.txt. We can use the file object file1. The code will perform all operations in the indent block, then close the file at the end of the indent. The method read stores the values of the file in the variable file_stuff as a string. You can print the file content. You can check if the file content is closed, but you cannot read from it outside the indent. But you can print the file content outside the indent as well. We can print the file content. We will see the following. When we examine the raw string, we will see the /n. This is so Python knows to start a new line. We can output every line as an element in a list using the method readLines. The first line corresponds to the first element in the list. The second line corresponds to the second element in the list, and so on. We can use the method readLine to read the first line of the file. If we run this command, it will store the first line in the variable file_stuff, then print the first line. We can use the method readLine twice. The first time it's called, it will save the first line in the variable file_stuff and then print the first line. The second time it's called, it will save the second line in the variable file_stuff and then print the second line. We can use a loop to print out each line individually as follows. Let's represent every character in a string as a grid. We can specify the number of characters we would like to read from a string as an argument to the method readLines. When we use a 4 as an argument in the method readLines, we print out the first 4 characters in the file. Each time we call the method, we will progress through the text. If we call the method with the argument 16, the first 16 characters are printed out and then the new line. If we call the method a second time, the next 5 characters are printed out. Finally, if we call the method the last time with the argument 9, the last 9 characters are printed out. Check out the labs for more examples of methods and other file types. We will use Python's open function to get a file object, to create a text file. We can apply method write to write data to that file. As a result, text will be written to the file. We can create the file example2.txt as follows. We use the open function. The first argument is the file path. This is made up of the file name. If you have that file in your directory, it will be overwritten, and the file directory. We set the mode parameter to W for writing. Finally, we have the file object. As before, we use the with statement. The code will run everything in the indent block, then close the file. We create the file object, file1. We use the open function. This creates a file example2.txt in your directory. We use the method write to write data into the file. The argument is the text we would like input into the file. If we use the write method successively, each time it's called, it will write to the file. The first time it is called, we will write, "This is line A" with a /n to represent a new line. The second time we call the method, it will write, "This is line B," then it will close the file. We can write each element in a list to a file. As before, we use a with command and the open function to create a file. The list lines has 3 elements consisting of text. We use a for loop to read each element of the first lines and pass it to the variable line. The first iteration of the loop writes the first element of the list to the file example2. The second iteration writes the second element of the list, and so on. At the end of the loop, the file will be closed. We can set the mode to appended using a lowercase a. This will not create a new file, but just use the existing file. If we call the method write, it will just write to the existing file, then add "This is line C," then close the file. We can copy one file to a new file as follows. First, we read the file example1 and interact with it via the file object, read file. Then we create a new file example3 and use the file object, write file to interact with it. The for loop takes a line from the file object, read file, and stores it in the file example3 using the file object, write file. The first iteration copies the first line. The second iteration copies the second line till the end of the file is reached. Then both files are closed. Check out the labs for more examples. We can import the library or a dependency like Pandas using the following command. We start with the import command, followed by the name of the library. We now have access to a large number of pre-built classes and functions. This assumes the library is installed. In our lab environment, all the necessary libraries are installed. Let's say we would like to load a CSV file using the Pandas built-in function, read CSV. A CSV is a typical file type used to store data. We simply type the word Pandas, then a dot and the name of the function with all the inputs. Typing Pandas all the time may get tedious. We can use the as statement to shorten the name of the library. In this case, we use the standard abbreviation PD. Now we type PD and a dot followed by the name of the function we would like to use. In this case, read_CSV. We are not limited to the abbreviation PD. In this case, we use the term banana. We will stick with PD for the rest of this video. Let's examine this code more in depth. One way Pandas allows you to work with data is with a data frame. Let's go over the process to go from a CSV file to a data frame. This variable stores the path of the CSV. It is used as an argument to the read_CSV function. The result is stored to the variable df. This is short for data frame. Now that we have the data in a data frame, we can work with it. We can use the method head to examine the first 5 rows of a data frame. The process for loading an Excel file is similar. We use the path of the Excel file. The function reads Excel. The result is a data frame. A data frame is comprised of rows and columns. We can create a data frame out of a dictionary. The keys correspond to the column labels. The values are lists corresponding to the rows. We then cast the dictionary to a data frame using the function dataFrame. We can see the direct correspondence between the table. The keys correspond to the table headers. The values are lists corresponding to the rows. We can create a new data frame consisting of 1 column. We just put the data frame name, in this case df, and the name of the column header enclosed in double brackets. The result is a new data frame comprised of the original column. You can do the same thing for multiple columns. We just put the data frame name, in this case df, and the name of the multiple column headers enclosed in double brackets. The result is a new data frame comprised of the specified columns. Consider the stack of 13 blocks of different colors. We can see there are 3 unique colors. Let's say you would like to find out how many unique elements are in a column of a data frame. This may be much more difficult because instead of 13 elements, you may have millions. Pandas has the method unique to determine the unique elements in a column of a data frame. Let's say we would like to determine the unique year of the albums in the data set. We enter the name of the data frame, then enter the name of the column released within brackets. Then we apply the method unique. The result is all of the unique elements in the column released. Let's say we would like to create a new database consisting of songs from the 1980s and after. We can look at the column released for songs made after 1979, then select the corresponding rows. We can accomplish this within one line of code in Pandas, but let's break up the steps. We can use the inequality operators for the entire data frame in Pandas. The result is a series of Boolean values. For our case, we simply specify the column released and the inequality for the albums after 1979. The result is a series of Boolean values. The result is true when the condition is true and false otherwise. We can select the specified columns in one line. We simply use the data frame's names, and in square brackets we place the previously mentioned inequality and assign it to the variable df1. We now have a new data frame, where each album was released after 1979. We can save the new data frame using the method to_CSV. The argument is the name of the CSV file. Make sure you include a .csv extension. There are other functions to save the data frame in other formats. Let's go over how to create a NumPy array. A Python list is a container that allows you to store and access data. Each element is associated with an index. We can access each element using a square bracket as follows. A NumPy array, or ND array, is similar to a list. It's usually fixed in size, and each element is of the same type, in this case integers. We can cast a list to a NumPy array by first importing NumPy. We then cast the list as follows. We can access the data via an index. As with the lists, we can access each element with an integer and a square bracket. The value of A is stored as follows. If we check the type of the array, we get numpy.ndArray. As NumPy arrays contain data of the same type, we can use the attribute dType to obtain the data type of the array's elements. In this case, a 64-bit integer. Let's review some basic array attributes using the array A. The attribute size is the number of elements in the array. As there are 5 elements, the result is 5. The next 2 attributes will make more sense when we get to higher dimensions, but let's review them. The attribute ndim represents the number of array dimensions or the rank of the array, in this case 1. The attribute shape is a tuple of integers indicating the size of the array in each dimension. We can create a NumPy array with real numbers. When we check the type of the array, we get numpy.ndArray. If we examine the attribute dType, we see float64 as the elements are not integers. There are many other attributes. Check out numpy.org. Let's review some indexing and slicing methods. We can change the first element of the array to 100 as follows. The array's first value is now 100. We can change the 5th element of the array as follows. The 5th element is now 0. Like lists and tuples, we can slice a NumPy array. The elements of the array correspond to the following index. We can select the elements from 1 to 3 and assign it to a new NumPy array, D, as follows. The elements in D correspond to the index. Like lists, we do not count the element corresponding to the last index. We can assign the corresponding indices to new values as follows. The array C now has new values. See the labs or numpy.org for more examples of what you can do with NumPy. NumPy makes it easier to do many operations that are commonly performed in data science. These same operations are usually computationally faster and require less memory in NumPy compared to regular Python. Let's review some of these operations on one-dimensional arrays. We will look at many of the operations in the context of Euclidean vectors to make things more interesting. Vector addition is a widely used operation in data science. Consider the vector u with two elements. The elements are distinguished by the different colors. Similarly, consider the vector v with two components. In vector addition, we create a new vector, in this case z. The first component of z is the addition of the first component of vectors u and v. Similarly, the second component is the sum of the second components of u and v. This new vector z is now a linear combination of the vector u and v. Representing vector addition with line segment or arrows is helpful. The first vector is represented in red. The vector will point in the direction of the two components. The first component of the vector is 1. As a result, the arrow is offset 1 unit from the origin in the horizontal direction. The second component is 0. We represent this component in the vertical direction. As this component is 0, the vector does not point in the vertical direction. We represent the second vector in blue. The first component is 0. Therefore, the arrow does not point to the horizontal direction. The second component is 1. As a result, the vector points in the vertical direction 1 unit. When we add the vector u and v, we get the new vector z. We add the first component. This corresponds to the horizontal direction. We also add the second component. It's helpful to use the tip-to-tail method when adding vectors, placing the tail of a vector v on the tip of vector u. The new vector z is constructed by connecting the base of the first vector u with the tail of the second v. The following 3 lines of code will add the two lists and place the result in the list z. We can also perform vector addition with 1 line of NumPy code. It would require multiple lines to perform vector subtraction on 2 lists as shown on the right side of the screen. In addition, the NumPy code will run much faster. This is important if you have lots of data. We can also perform vector subtraction by changing the addition sign to a subtraction sign. It would require multiple lines to perform vector subtraction on 2 lists, as shown on the right side of the screen. Vector multiplication with a scalar is another commonly performed operation. Consider the vector y. Each component is specified by a different color. We simply multiply the vector by a scalar value, in this case 2. Each component of the vector is multiplied by 2. In this case, each component is doubled. We can use the line segment or arrows to visualize what's going on. The original vector y is in purple. After multiplying it by a scalar value of 2, the vector is stretched out by 2 units, as shown in red. The new vector is twice as long in each direction. Vector multiplication with a scalar only requires 1 line of code using NumPy. It would require multiple lines to perform the same task as shown with Python lists as shown on the right side of the screen. In addition, the operation would also be much slower. Hadamard product is another widely used operation in data science. Consider the following 2 vectors, u and v. The Hadamard product of u and v is a new vector z. The first component of z is the product of the first element of u and v. Similarly, the second component is the product of the second element of u and v. The resultant vector consists of the entry-wise product of u and v. We can also perform Hadamard product with 1 line of code in NumPy. It would require multiple lines to perform Hadamard product on 2 lists as shown on the right side of the screen. The dot product is another widely used operation in data science. Consider the vector u and v. The dot product is a single number given by the following term and represents how similar 2 vectors are. We multiply the first component from v and u. We then multiply the second component and add the result together. The result is a number that represents how similar the 2 vectors are. We can also perform dot product using the NumPy function dot and assign it with the variable result as follows. Consider the array U. The array contains the following elements. If we add a scalar value to the array, NumPy will add that value to each element. This property is known as broadcasting. A universal function is a function that operates on ND arrays. We can apply a universal function to a NumPy array. Consider the arrays A. We can calculate the mean or average value of all the elements in A using the method mean. This corresponds to the average of all the elements. In this case, the result is 0. There are many other functions. For example, consider the NumPy arrays B. We can find the maximum value using the method 5. We see the largest value is 5. Therefore, the method max returns a 5. We can use NumPy to create functions that map NumPy arrays to new NumPy arrays. Let's implement some code on the left side of the screen and use the right side of the screen to demonstrate what's going on. We can access the value of pi in NumPy as follows. We can create the following NumPy array in radians. This array corresponds to the following vector. We can apply the function sine to the array x and assign the values to the array y. This applies the sine function to each element in the array. This corresponds to applying the sine function to each component of the vector. The result is a new array y, where each value corresponds to a sine function being applied to each element in the array x. A useful function for plotting mathematical functions is line space. Line space returns evenly spaced numbers over a specified interval. We specify the starting point of the sequence, the ending point of the sequence. The parameter num indicates the number of samples to generate. In this case, 5. The space between samples is 1. If we change the parameter num to 9, we get 9 evenly spaced numbers over the interval from -2 to 2. The result is the difference between subsequent samples is 0.5 as opposed to 1 as before. We can use the function linespace to generate 100 evenly spaced samples from the interval 0 to 2 pi. We can use the NumPy function sine to map the array x to a new array y. We can import the library pyplot as plt to help us plot the function. As we are using a Jupyter notebook, we use the command matplotlib inline to display the plot. The following command plots a graph. The first input corresponds to the values for the horizontal or x-axis. The second input corresponds to the values for the vertical or y-axis. There's a lot more you can do with NumPy. Check out the labs at numpy.org for more. Consider the list A. The list contains 3 nested lists, each of equal size. Each list is color-coded for simplicity. We can cast the list to a NumPy array as follows. It is helpful to visualize the NumPy array as a rectangular array. Each nested list corresponds to a different row of the matrix. We can use the attribute ndim to obtain the number of axes or dimensions referred to as the rank. The term rank does not refer to the number of linearly independent columns like a matrix. It's useful to think of ndim as the number of nested lists. The first list represents the first dimension. This list contains another set of lists. This represents the second dimension or axes. The number of lists the list contains does not have to do with the dimension, but the shape of the list. As with the 1D array, the attribute shape returns a tuple. It's helpful to use the rectangular representation as well. The first element in the tuple corresponds to the number of nested lists contained in the original list or the number of rows in the rectangular representation, in this case 3. The second element corresponds to the size of each of the nested lists or the number of columns in the rectangular array 0. The convention is to label this axis 0 and this axis 1 as follows. We can also use the attribute size to get the size of the array. We see there are 3 rows and 3 columns. Multiplying the number of columns and rows together, we get the total number of elements. In this case, 9. Check out the labs for arrays of different shapes and other attributes. We can use rectangular brackets to access the different elements of the array. The following image demonstrates the relationship between the indexing conventions for the list like representation. The index in the first bracket corresponds to the different nested lists, each a different color. The second bracket corresponds to the index of a particular element within the nested list. Using the rectangular representation, the first index corresponds to the row index. The second index corresponds to the column index. We can also use a single bracket to access the elements as follows. Consider the following syntax. This index corresponds to the second row, and this index the third column. The value is 23. Consider this example. This index corresponds to the first row, and the second index corresponds to the first column, and a value of 11. We can also use slicing in NumPy arrays. The first index corresponds to the first row. The second index accesses the first two columns. Consider this example. The first index corresponds to the first two rows. The second index accesses the last column. We can also add arrays. The process is identical to matrix addition. Consider the matrix X. Each element is colored differently. Consider the matrix Y. Similarly, each element is colored differently. We can add the matrices. This corresponds to adding the elements in the same position, i.e. adding elements contained in the same color boxes together. The result is a new matrix that is the same size as matrix Y or X. Each element in this new matrix is the sum of the corresponding elements in X and Y. To add two arrays in NumPy, we define the array, in this case, X. Then we define the second array, Y. We add the arrays. The result is identical to matrix addition. Multiplying a NumPy array by a scalar is identical to multiplying a matrix by a scalar. Consider the matrix Y. If we multiply the matrix by the scalar 2, we simply multiply every element in the matrix by 2. The result is a new matrix of the same size where each element is multiplied by 2. Consider the array Y. We first define the array. We multiply the array by a scalar as follows and assign it to the variable z. The result is a new array where each element is multiplied by 2. Multiplication of two arrays corresponds to an element Y's product or Hadamard product. Consider array X and array Y. Hadamard product corresponds to multiplying each of the elements in the same position, i.e. multiplying elements contained in the same color boxes together. The result is a new matrix that is the same size as matrix Y or X. Each element in this new matrix is the product of the corresponding elements in X and Y. Consider the array X and Y. We can find the products of two arrays X and Y in one line and assign it to the variable z as follows. The result is identical to Hadamard product. We can also perform matrix multiplication with NumPy arrays. Matrix multiplication is a little more complex, but let's provide a basic overview. Consider the matrix A, where each row is a different color. Also, consider the matrix B, where each column is a different color. In linear algebra, before we multiply matrix A by matrix B, we must make sure that the number of columns in matrix A, in this case 3, is equal to the number of rows in matrix B, in this case 3. For matrix multiplication, to obtain the ith row and jth column of the new matrix, we take the dot product of the ith row of A with the jth columns of B. For the first column, first row, we take the dot product of the first row of A with the first column of B as follows. The result is 0. For the first row and the second column of the new matrix, we take the dot product of the first row of the matrix A, but this time we use the second column of matrix B. The result is 2. For the second row and the first column of the new matrix, we take the dot product of the second row of the matrix A with the first column of matrix B. The result is 0. Finally, for the second row and the second column of the new matrix, we take the dot product of the second row of the matrix A with the second column of matrix B. The result is 2. In NumPy, we can define the NumPy arrays A and B. We can perform matrix multiplication and assign it to array C. The result is the array C. It corresponds to the matrix multiplication of array A and B. There is a lot more you can do with it in NumPy. Check out numpy.org.
An API lets two pieces of software talk to each other. For example, you have your program, you have some data, and you have other software components. You use the API to communicate with other software via inputs and outputs. Just like a function, you don't have to know how the API works, just its inputs and outputs. Pandas is actually a set of software components, much of which are not even written in Python. You have some data, you have a set of software components. We use the Pandas API to process the data by communicating with the other software components. Let us clean up the diagram. When you create a dictionary, then create a Pandas object with the data frame constructor, in API lingo, this is an instance. The data in the dictionary is passed along to the Pandas API. You then use the data frame to communicate with the API. When you call the method head, the data frame communicates with the API displaying the first few rows of the data frame. When you call the method mean, the API will calculate the mean and return the values. REST APIs are another popular type of API. They allow you to communicate through the internet, letting you take advantage of resources like storage, access more data, artificial intelligence algorithms, and much more. The RE stands for representational, the S for state, and T for transfer. In REST APIs, your program is called the client. The API communicates with a web service you call through the internet. There is a set of rules regarding communication: input or request, and output or response. Here are some common terms. You or your code can be thought of as a client. The web service is referred to as a resource. The client finds the service via an endpoint. We will review this more in the next section. The client sends requests to the resource and the response to the client. HTTP methods are a way of transmitting data over the internet. We tell the REST APIs what to do by sending a request. The request is usually communicated via an HTTP message. The HTTP message usually contains a JSON file. This contains instructions for what operation we would like the service to perform. This operation is transmitted to the web service via the internet, and the service performs the operation. In a similar manner, the web service returns a response via an HTTP message where the information is usually returned via a JSON file, and this information is transmitted back to the client. Cryptocurrency data is excellent to use in an API because it is constantly updated and is vital to cryptocurrency trading. We will use the PyCoinGecko Python client, or wrapper, for the CoinGecko API, updated every minute by CoinGecko. We use the wrapper, or client, because it is easy to use so you can focus on the task of collecting data. We will also introduce Pandas time series functions for dealing with time series data. Using PyCoinGecko to collect data is simple. All we need is to install and import the library, then create a client object, and finally use a function to request our data. In this function, we are getting data on Bitcoin in US dollars for the past 30 days. In this case, our response is a JSON file expressed as a Python dictionary of nested lists, including price, market cap, and total volumes, which contain the Unix timestamp and the price at the time. We are only interested in price, so that is what we will select using the key price. To make things simple, we can convert our nested list to a data frame. With the column's timestamp and price, it is difficult to understand the column timestamp. We will convert it to a more readable format using the pandas function to_datetime. Using this to_datetime function, we create readable time data. The input is the timestamp column. Unit of time is set to milliseconds. We append the output to the new column date. Now we want to create a candlestick plot. To get the data for the daily candlesticks, we will group by the date to find the minimum, maximum, first, and last price of each day. Finally, we will use Plotly to create the candlestick chart and plot it.
We will transcribe an audio file using the Watson Text-to-Speech API. We will then translate the text to a new language using the Watson Language Translator API. In the API call, you will send a copy of the audio file to the API. This is sometimes called a POST request. Then the API will send the text transcription of what the individual is saying. Under the hood, the API is making a GET request. We then send the text we would like to translate into a second language to a second API. The API will translate the text and send the translation back to you. In this case, we translate English to Spanish. We then provide an overview of API keys and endpoints, Watson Speech-to-Text, and Watson Translate. First, we will review API keys and endpoints. They will give you access to the API. An API key is a way to access the API. It's a unique set of characters that the API uses to identify you and authorize you. Usually your first call to the API includes the API key. This will allow you access to the API. In many APIs, you may get charged for each call, so like your password, you should keep your API key a secret. An endpoint is simply the location of the service. It's used to find the API on the internet, just like a web address. Now we will transcribe an audio file using the Watson Text-to-Speech API. Before you start the lab, you should sign up for an API key. We will download an audio file into your directory. First, we import Speech-to-Text v1 from IBM Watson. The service endpoint is based on the location of the service instance. We store the information in the variable URL_S2T. To find out which URL to use, view the service credentials. You will do the same for your API key. You create a speech-to-text adapter object. The parameters are the endpoint and API key. You will use this object to communicate with the Watson speech-to-text service. We have the path of the WAV file we would like to convert to text. We create the file object WAV with the WAV file using Open. We set the mode to RB, which means to read the file in binary format. The file object allows us access to the WAV file that contains the audio. We use the method recognize from the speech-to-text adapter object. This basically sends the audio file to Watson's speech-to-text service. The parameter audio is the file object. The content type is the audio file format. The service sends a response stored in the object response. The attribute result contains a Python dictionary. The key results value has a list that contains a dictionary. We are interested in the key transcript. We can assign it to the variable recognized_text as follows. Recognized_text now contains a string with the transcribed text. Now let's see how to translate the text using the Watson Language Translator. First, we import Language Translator v3 from IBM_Watson. We assign the service endpoint to the variable URL_LT. You can obtain the service in the lab instructions. You require an API key. See the lab instructions on how to obtain the API key. This API request requires the date of the version. See the documentation. We create a language translator object, Language Translator. We can get a list of the languages that the service can identify as follows. The method returns the language code. For example, English has a symbol EN to Spanish, which has the symbol ES. In the last section, we assign the transcribed text to the variable to recognized_text. We can use the method translate. This will translate the text. The result is a detailed response object. The parameter text is the text. Model_ID is the type of model we would like to use. In this case, we set it to EN-ES for English to Spanish. We use the method getResult to get the translated text and assign it to the variable translation. The result is a dictionary that includes the translation word count and character count. We can obtain the translation and assign it to the variable Spanish_translation as follows. Using the variable Spanish_translation, we can translate the text back to English as follows. The result is a dictionary. We can obtain the string with the text as follows. We can then translate the text to French as follows.
We touched on REST APIs in the last section. The HTTP protocol can be thought of as a general protocol of transferring information through the web. This includes many types of REST APIs. Recall that REST APIs function by sending a request, and the request is communicated via HTTP message. The HTTP message usually contains a JSON file. When you, the client, use a web page, your browser sends an HTTP request to the server where the page is hosted. The server tries to find the desired resource, by default index.html. If your request is successful, the server will send the object to the client in an HTTP response. This includes information like the type of the resource, the length of the resource, and other information. The table under the web server represents a list of resources stored in the web server. In this case, an HTML file, PNG image, and a text file. When the request is made for the information, the web server sends the requested information, that is, one of the files. A Uniform Resource Locator, or URL, is the most popular way to find resources on the web. We can break the URL into 3 parts. First, we have the scheme. This is the protocol, and for this lab, it will always be http://. The internet address, or base URL. This will be used to find the location. Some examples include www.ibm.com and www.gitlab.com. And finally, the route. This is the location on the web server. For example, /images/idsnlogo.png. Let us review the request and response process. The following is an example of the request message for the GetRequest method. There are other HTTP methods we can use. In the start line, we have the GET method. This is an HTTP method. In this case, it's requesting the file index.html. The request header passes additional information with an HTTP request. In the GET method, the request header is empty. Some requests have a body. We will have an example of a request body later. The following table represents the response. The response start line contains the version number followed by a descriptive phrase. In this case, HTTP/1.0, a status code, 200, meaning success, and the descriptive phrase, OK. We have more on status codes later. The response header contains information. Finally, we have the response body containing the requested file, in this case, an HTML document. Let us look at other status codes. Some status code examples are shown in the table below. The prefix indicates the class. For example, the 100s are informational responses. 100 indicates that everything is okay so far. The 200s are successful responses. For example, 200, the request has succeeded. Anything in the 400s is bad news. 401 means the request is unauthorized. 500s stand for server errors, like 501 for not implemented. When an HTTP request is made, an HTTP method is sent. This tells the server what action to perform. A list of several HTTP methods is shown here. In the next video, we will use Python to apply the GET method that retrieves data from the server and the POST method that sends data to the server. Let us review the request module in Python. This is one of several libraries, including httplib and urllib, that can work with the HTTP protocol. Requests is a Python library that allows you to send HTTP/1.1 requests easily. We can import the library as follows. You can make a GET request via the method GET to www.ibm.com. We have the response object R. This has information about the request, like the status of the request. We can view the status code using the attribute status_code, which is 200 for OK. You can view the request headers. You can view the request body in the following line. As there is no body for a GET request, we get a none. You can view the HTTP response header using the attribute headers. This returns a Python dictionary of HTTP response headers. We can look at the dictionary values. We can obtain the date the request was sent by using the key date. The key content type indicates the type of data. Using the response object R, we can also check the encoding. As the content type is text or HTML, we can use the attribute text to display the HTML in the body. We can review the first 100 characters. You can also download other content. See the lab for more. You can use the get method to modify the results of your query. For example, retrieving data from an API. In the lab, we will use http://bin.org, a simple HTTP request and response service. We send a GET request to the server. Like before, we have the base URL in the route. We append /get. This indicates we would like to perform a GET request. This is demonstrated in the following table. After GET is requested, we have the query string. This is part of a Uniform Resource Locator, or URL, and this sends other information to the web server. The start of the query is a question mark, followed by a series of parameter and value pairs, as shown in the table below. The first parameter name is name, and the value is Joseph. The second parameter name is ID, and the value is 123. Each pair, parameter, and value is separated by an equal sign. The series of pairs is separated by the ampersand. Let us complete an example in Python. We have the base URL with get appended to the end. To create a query string, we use the dictionary payload. The keys are the parameter names, and the values are the value of the query string. Then we pass the dictionary payload to the params parameter of the get function. We can print out the URL and see the name and values. We can see the request body. As the info is sent in the URL, the body has a value of none. We can print out the status code. We can view the response as text, and we can look at the key content type to look at the content type. As the content type is in the JSON, we format it using the method JSON. It returns a Python dict. The key args has the name and values for the query string. Like a GET request, a POST request is used to send data to a server, but the POST request sends the data in a request body, not the URL. In order to send the POST request in the URL, we change the route to POST. This endpoint will expect data, and it is a convenient way to configure an HTTP request to send data to a server. We have the payload dictionary. To make a POST request, we use the POST function. The variable payload is passed to the parameter data. Comparing the URL using the attribute URL from the response object of the GET and POST request, we see the POST request has no name or value pairs in its URL. We can compare the POST and GET request body. We see only the POST request has a body, and we can view the key form to get the payload. Lots of useful data is available on web pages, such as real estate prices and solutions to coding questions. The website Wikipedia is a repository of the world's information. If you have an understanding of HTML, you can use Python to extract this information. In this video, you will review the HTML of a basic web page, understand the composition of an HTML tag, understand HTML trees, and understand HTML tables. Let us say you had a request to find the name and salary of players in a national basketball league from the following page. The web page is comprised of HTML. It consists of text surrounded by a series of blue text elements enclosed in angle brackets called tags. The tags tell the browser how to display the content. The data we require is in this text. The first portion contains the doctype HTML, which declares this document is an HTML document. HTML element is the root element of an HTML page, and head element contains meta information about the HTML page. Next, we have the body. This is what is displayed on the web page. This is usually the data we are interested in. We see the elements with an H3. This means type 3 heading, which makes the text larger and bold. These tags have the names of the players. Notice the data is enclosed in the elements. It starts with an H3 in brackets and ends in a /H3 in brackets. There is also a different tag, P. This means paragraph. Each P tag contains a player's salary. Let us take a closer look at the composition of an HTML tag. Here is an example of an HTML anchor tag. It will display IBM, and when you click it, it will send you to ibm.com. We have the tag name, in this case, A. This tag defines a hyperlink, which is used to link from one page to another. It is helpful to think of each tag name as a class in Python and each individual tag as an instance. We have an opening or start tag, and we have the end tag. This has the tag name preceded by a slash. These tags contain the content, in this case, what is displayed on the web page. We have the attribute. This is composed of the attribute name and attribute value. In this case, it is the URL to the destination web page. Real web pages are more complex, and depending on your browser, you can select the HTML element, then click Inspect. The result will give you the ability to inspect the HTML. There is also other types of content, such as CSS and JavaScript, that we will not go over in this course. The actual element is shown here. Each HTML document can actually be referred to as a document tree. Let us go over a simple example. Tags may contain strings and other tags. These elements are the tag's children. We can represent this as a family tree. Each nested tag is a level in the tree. The tag HTML tag contains the head and body tag. The head and the body tag are the descendants of the HTML tag. In particular, they are the children of the HTML tag. HTML tag is their parent. The head and body tag are siblings as they are on the same level. Title tag is the child of the head tag, and its parent is the head tag. The title tag is a descendant of the HTML tag, but not its child. The heading and paragraph tags are the children of the body tag, and as they are all children of the body tag, they are siblings of each other. The bold tag is a child of the heading tag. The content of the tag is also part of the tree, but this can get unwieldy to draw. Next, let us review HTML tables. To define an HTML table, we have the table tag. Each table row is defined with a TR tag, and you can also use a table header tag for the first row. The table row cell contains a set of TD tags. Each defines a table cell. For the first row, first cell, we have. For the first row, second cell, we have. And so on. For the second row, we have. And for the second row, first cell, we have. And for the second row, second cell, we have. And so on. We now have some basic knowledge of HTML. Now let us try and extract some data from a web page. What would you do if you wanted to analyze hundreds of points of data to find the best players of a sports team? Would you start manually copying and pasting information from different websites into a spreadsheet, spending hours trying to find the right data, and eventually giving up because the task was too overwhelming? That is where web scraping can help. Web scraping is a process that can be used to automatically extract information from a website, and can easily be accomplished within a matter of minutes and not hours. To get started, we just need a little Python code and the help of two modules named Requests and Beautiful Soup. Let us say you were asked to find the name and salary of players in a national basketball league from the following web page. First, we import Beautiful Soup. We can store the web page HTML as a string in the variable HTML. To parse a document, pass it into the Beautiful Soup constructor. We get the Beautiful Soup object, soup, which represents the document as a nested data structure. Beautiful Soup represents HTML as a set of tree-like objects with methods used to parse the HTML. We will review the Beautiful Soup object. Using the Beautiful Soup object, soup, we created. The tag object corresponds to an HTML tag in the original document, for example, the tag title. Consider the tag h3. If there is more than one tag with the same name, the first element with that tag is selected. In this case, with LeBron James, we see the name is enclosed in the bold attribute B. To extract it, use the tree representation. So let us use the tree representation. The variable tag-object is located here. We can access the child of the tag or navigate down the branch as follows. You can navigate up the tree by using the parent attribute. The variable tag child is located here, and we can access the parent. This is the original tag object. We can also find the sibling of tag object. We simply use the next -sibling attribute. We can find the sibling of sibling 1. We simply use the next sibling attribute. Consider the tag-child object. You can access the attribute name and value as a key value pair in a dictionary as follows. You can return the content as a navigable string. This is like a Python string that supports Beautiful Soup functionality. Now let us review the method findAll. This is a filter. You can use filters to filter based on a tag's name, its attributes, the text of a string, or on some combination of these. And consider the list of pizza places. Like before, create a Beautiful Soup object, but this time name it table. The find_all method looks through a tag's descendants and retrieves all descendants that match your filters. Apply it to the table with the tag tr. The result is a Python iterable just like a list. Each element is a tag object for tr. This corresponds to each row in the list, including the table header. Each element is a tag object, so consider the first row. For example, we can extract the first table cell. We can also iterate through each table cell. First, we iterate through the list table rows via the variable row. Each element corresponds to a row in the table. We can apply the method findAll to find all the table cells. Then we can iterate through the variable cells for each row. For each iteration, the variable cell corresponds to an element in the table for that particular row. And we continue to iterate through each element and repeat the process for each row. Let us see how to apply Beautiful Soup to a web page. To scrape a web page, we also need the requests library. The first step is to import the modules that are needed. Use the get method from the requests library to download the web page. The input is the URL. Use the text attribute to get the text and assign it to the variable page. Then create a Beautiful Soup object, soup, from the variable page. It will allow you to parse through the HTML page, and you can now scrape the page. Collecting data, you will find there are many different file formats that need to be collected or read in order to complete a data-driven story or analysis. When gathering the data, Python can make the process simpler with its predefined libraries. But before we explore Python, let us first check out some of the various file formats. Looking at a file name, you will notice an extension at the end of the title. These extensions let you know what type of file it is and what is needed to open it. For instance, if you see a title like fileexample.csv, you will know this is a CSV file. But this is only one example of different file types. There are many more, such as JSON or XML. When coming across these different file formats and trying to access their data, we need to utilize Python libraries to make this process easier. The first Python library to become familiar with is called Pandas. By importing this library in the beginning of the code, we are then able to easily read the different file types. Since we have now imported the Panda library, let us use it to read the first CSV file. In this instance, we have come across the fileexample.csv file. The first step is to assign the file to a variable. Then, create another variable to read the file with the help of the Panda library. We can then call read_CSV function to output the data to the screen. With this example, there were no headers for the data, so it added the first line as the header. Since we do not want the first line of data as the header, let us find out how to correct this issue. Now that we have learned how to read and output the data from a CSV file, let us make it look a little more organized. From the last example, we were able to print out the data, but because the file had no headers, it printed the first line of data as the header. We easily solve this by adding a data frame attribute. We use the variable df to call the file, then add the columns attribute. By adding this one line to our program, we can then neatly organize the data output into the specified headers for each column. The next file format we will explore is the JSON file format. In this type of file, the text is written in a language-independent data format and is similar to a Python dictionary. The first step in reading this type of file is to import JSON. After importing JSON, we can add a line to open the file, call the load attribute of JSON to begin, and read the file. And lastly, we can then print the file. The next file format type is XML, also known as Extensible Markup Language. While the Pandas library does not have an attribute to read this type of file, let us explore how to parse this type of file. The first step to read this type of file is to import XML. By importing this library, we can then use the eTree attribute to parse the XML file. We then add the column headers and assign them to the data frame. Then create a loop to go through the document to collect the necessary data and append the data to a data frame.